Hello everyone. In this class we will discuss few concepts related to nucleus. Composition, most of you are already aware of. Size, density and nuclear forces. The concept of nucleus was given by Rutherford when he was explaining the observations of Geiger and Marsden experiment, that the entire positive charge and almost entire mass of the atom is concentrated at the center of the atom, and he named it nucleus. He also estimated the size of the nucleus. So as per the informations that we have today, nucleus consists of protons and neutrons. Protons have positive charge, neutrons are neutral, and the mass of the neutron is slightly more than the mass of proton. Mass of proton is nearly 1.0073 atomic mass unit, while neutron it is 0087. Mass of electron, which revolves around the nucleus, it is around 0.00055 electron volt. Atomic mass unit. So these are the masses of protons, neutrons and electrons. Okay, now size R is equal to R naught A 1 by 3, where R naught is, this is the radius of the nucleus. It is 1.1 femtometer or Fermi, which is 1.1 into 10 raised to the power minus 15 meters. A is the mass number, means number of neutron plus proton, number of nucleons in the nucleus. If I have to find out the density of the nuclear matter, then density is mass upon volume. And what will be the mass of the nucleus? If I take the mass of the neutron and proton almost same, then I can say it is the number of nucleons present into mass of one nucleon. I will take it around 1 AMU divided by volume, considering it again perfectly spherical, 4 by 3 pi r cube. So I can substitute all these values. A mass will be 1.67 into 10 raised to the power minus 27 kg divided by 4 by 3 pi, and r cube means r naught cube A. It comes out to be nearly, I'm telling you the order, some value here into 10 raised to the power 70. What is important is that the density of nuclear matter does not depend on A, mass number. So whether we are taking a light nucleus or we are taking a heavy nucleus, density is same. It does not depend on that. The mass will depend, obviously. More number of nucleons means it will be heavier. Size will also be different, but density will remain same. Density is independent of A. Sometimes even this question is asked in exam. Show that the density of nuclear matter is constant or independent of the mass number. Then you can just show it, mass upon volume. We have assumed that mass of proton and neutron is almost same, and I have taken it 1 AMU. 1 AMU is this much in kilogram. And I have assumed that the nucleus is perfectly spherical. So 4 by 3 pi r cube and r given from here. So it's all about the composition, size and density. Now let's talk about the nuclear forces. Let's talk about the nuclear forces now. See, we know that positive charge, if we bring another positive charge close to a positive charge, what happens? There is a force of repulsion, electrostatic repulsion, governed by Coulomb's law. And this force becomes zero only at infinity. We call them large range forces. And the force is very, very strong when the particles are very close. Now just imagine, we have said that the size of a nucleus is in femtometer, 10 raised to power minus 15 meter order. That's the order. So it means so many protons are living inside the nucleus despite the strong repulsive forces. Repulsive forces are very strong. That constant of proportionality is 9 into 10 raised to power 9. So these forces are very strong. So despite these repulsive forces, how can the protons live inside the nucleus? This repulsive force should take them away. It should not let the nucleus be formed because of these repulsive forces. So this clearly indicates that it means there is some another force which counters this repulsive force and helps in the formation of a nucleus. These forces are attractive in nature so that they can overcome this repulsive force, and are very strong forces. These forces we call nuclear forces. So nuclear forces are the forces acting between the nucleons. Now, what are the properties of these forces? Let us discuss them. They are attractive in nature. So these forces are attractive, that's why they counter the repulsive force and are operative at a distance of around 1 femtometer. So if we plot a potential energy versus distance between two nucleons, then see at around 0.8 femtometer, the potential energy is most negative or minimum. If the distance is further increased, then see now this potential energy is approaching 0, and after that it is positive. Positive means repulsive force. And here it is repulsive force, and here it becomes 0 also. So it means these forces are mostly attractive in nature, but if the distance between the nucleons is very, very small, much smaller than even 0.8 Fermi, then these forces have a repulsive component. Otherwise the nucleus would have been crushed to just a point, but this has a finite size, which means at a very, very less distance they have this repulsive component, and further these forces become 0 also. At a distance of about 10 femtometer, this force is 0. So these forces in a way they don't obey the inverse square law. We don't have direct expression of nuclear force between two nucleons as simpler as we have for electrostatic force between two charges, or the gravitational force between 2 point masses. So these forces are complex in nature. So they are attractive mostly and very strong forces. The strongest forces in nature. They are about 50 to 60 times stronger than electromagnetic forces. So much stronger. They are the strongest forces in nature. Short range force. This I explained here also, that at a distance of around 10 Fermi it is 0. This we call short range force or saturation of the forces. So a particular nucleon inside a nucleus is attracted by only neighboring nucleons, not by all nucleons present inside the nucleus. So if we take a very happy nucleus and we just want to find out what is the nuclear force at any one nucleon at the center of the nucleus, then those nucleons which are at the boundary of the nucleus, they don't exert any attractive force. So this force is only by neighboring nucleons. Charge independent, which means it has nothing to do whether the particle is proton or neutron. So act equally between proton, neutron, 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 or proton, proton. So this force acts equally between all these pairs. It has nothing to do with charge, but spin dependent. We know that these particles, proton and neutron, also have a spin. So if there are two nucleons with plus half and plus half, or minus half and minus half, this force is stronger than when the spin is plus half and minus half. So charge independent but spin dependent. A Japanese scientist Yukawa also told about one more nature of these forces, that they are the exchange forces. Exchange forces means that between two nucleons, it is because of the transfer of one particle from one nucleon to other nucleon. It is just like if we have two children and one is throwing a ball onto the other. So what happens? If a moving ball is coming to you, you stop it. There is a transfer of momentum conservation. Transfer of momentum is equivalent to force. F is equal to dp by dt. So if two students are standing and they are throwing ball, one is throwing, other is catching, and then the other is throwing, it is equivalent to a force between them. So nucleons, they attract each other due to the exchange of one particle, meson theory here. So these are the important properties of nuclear forces. Attractive in nature, strongest forces, short range forces, charge independent, spin dependent, and they are the exchange forces. Now a little bit about the stability of a nucleus. How, see, just as we have different energy levels for electrons in an atom, same way, even inside a nucleus, we have energy levels for the nucleons. And here also, we use Pauli's exclusion principle to fill these energy states. In every energy state, we can have two protons and two neutrons with opposite spins. And filling starts from the lowest. So here I have taken the example of boron and calcium. Carbon 6C12 and boron 5B12. Here we have 5 protons, 7 neutrons, 6 protons, 6 neutrons, and I have made this level. So how the filling starts, you can see 2 protons, then 2, then 1. It makes it 5. For neutron, 2, 2, 2, and then 1. So one neutron goes up to higher state. And here, they all are accommodated in just 3 levels. So this one has more energy than this. This will be more unstable. This is more stable than this. So these nucleons have a tendency to pair up. 2 neutrons, 2 protons, they pair up. In lighter nuclei, it has been observed that all those which are stable have equal number of neutrons and protons. So I can say 2He4, 6C12, 8O16. They are more stable than their neighbors. But as the number keeps on increasing, if we take a heavy nucleus, then that nucleus cannot be stable if the number of neutrons and protons are same, because of the nature of nuclear forces. They are short range forces. So it means if the nucleus is very heavy, then what will happen? If the size of the nucleus is very large and I take one proton at the center, this will be repelled by all protons present inside. I have drawn randomly. So this proton will be repelled by all, or this proton will be repelled by all other protons, but will be attracted only by neighbors. So these repulsive pairs, they are increased. So to balance it, more number of neutrons are required. So in heavy nuclei, the number of neutrons is always more than the number of protons. We can take the example of, say, uranium 92 to 35. In same way, you can see all heavier, as the mass number keeps on increasing, the number of neutrons is more than the number of protons, so that the repulsive force can be counterbalanced by the more number of attractive pairs. Neutrons will not participate in repulsion, but there is a limit even to that, because if the number of neutrons keep on increasing, there will be no protons to get paired up. So there is a limit up to it. Bismuth 206, that is the most stable heavy nuclide. If we go beyond it, they try to get stability by emitting radiation. This is what radioactivity is. So that's enough about nuclear forces as far as your syllabus is concerned. Thank you.